We are going to continue with our discussion of chapter 10 today, which is what happens when a pi bond acts as a nucleophile to attack an electrophile. And remember, there's some basic issues here, two sets of issues. One is regioselectivity, that is, of the atoms in the pi bond, A and B, which one gets the new sigma bond in the first step, and that's related to which one gets the positive charge in the intermediate. And then the second issue is one of stereoselectivity. Alkenes have to be able to react from above or below with the same rate. And then if you have a carbocationic intermediate, you can attack the empty p orbital on that carbocation either from above or below. So we tried to illustrate those issues with this example. We took a cyclohexane ring where hexene ring with a pi bond between carbons A and B. A has a methyl group, D has deuterium. Recall that deuterium is exactly the same as hydrogen, only it's got a neutron in the nucleus where hydrogen does not. So it weighs just a little bit more. Chemically, it's identical to hydrogen, but you can tell the difference between the two. And we're using this to illustrate both the regio and the stereochemical issues associated with this reaction. Notice that in the first step, when HOMO attacks LUMO, or the pi bond attacks the hydrogen, you get the hydrogen on the same carbon as deuterium. The reason for that is so that the positive charge can be on the more substituted carbon where it's more stable. Notice as well that we get products, we get intermediates here that come from hydrogen being added to the top face of this alkene versus the bottom face of this alkene. You have to get both of those. You can't just get one. The starting material was not chiral. Here we've now made a stereocenter in our intermediate, so you have to get both configurations. Then we get this intermediate with the positive charge on the more substituted carbon. We've called that Markovnikov selectivity. That's the Markovnikov rule. That Cl- can attack from above or below. So from the carbocation on the left, we get these two products, one in which Cl has added from above and the other where it's added from below. And then from the carbocation on the right, we get these two products. Again, one where Cl- is added from above or below. So you get four products here. And you can see where those four products come from. They come from the two times in the reaction where something can happen from either side of a molecule. In the first step, that first addition step can happen from either side. And in the second step, nucleophilic attack can happen from either side. So we want to look at these four products. Some of them are enantiomers of each other. For example, we'll call this A, B, C, and D. A and D are enantiomers, just like B and C are enantiomers. But there's some diastereomer relationships too, and to illustrate that, I'm going to highlight the two things that got added to the alkene. One was the chloro and the other was the hydrogen. Okay? So I'm going to highlight the hydrogens in blue and then highlight the chloros in purple. And you can see that in some of the cases, in A and D, hydrogen and chloro are on the same side of the molecule, on the same side of the original alkene. So we would call these syn products, SYN for same. Those are syn products. And then in B and C, the hydrogen and the chloro are anti to each other. we would call those, they are opposite each other, they are trans to each other. We're going to call those anti-products. Okay? Notice that all of the syn products are diastereomers with all of the anti-products. And notice in this reaction there is no selectivity for syn versus anti-products. That's important because we're going to contrast this in the near future with a reaction where there is selectivity for an anti-product or where there is selectivity for a syn product. If you were trying to save time, you could draw all of these four products with, you could indicate all four products with a fairly simple drawing that looked like this, where instead of dashes and wedges, you use straight lines. That's fine. I chose not to do that here because I wanted to illustrate the syn and anti-products that form as a result of this reaction. That's hard to do if you don't use dashes or wedges. Okay? Questions about that particular reaction? Yeah?
Could you just help me see like the syn with A and D? Because like the one scale was like a wedge and one scale is a dash. Like on A it's a wedge, on D it's a dash. Would that be
A and D are syn products. You are right that C is not a syn product.
Okay. Or for A and D.
Yeah.
Because would they be anti, like one group is like a wedge and one group is a dash?
So the two groups that got added are this chloro and this hydrogen, and both are wedges.
Yep.
And then in D, the two groups that got added are this chloro and this hydrogen, and both are dashes.
Got it. Okay.
Yep, so we're talking about the relationship between the highlighted groups. Notice that in B and C, one is a dash and one is a wedge.
Got it. Thank you so much.
Yep, you bet. Others? Okay, well, so you could do a similar set of reaction conditions. We'll take, you'll see lots of different examples of starting materials in their book. They're all in your book. They're all alkenes. In this case, I'm going to stick with our alkene starting material. And we'll stick with the deuterium just because this particular example really illustrates the syn and anti issues. Instead of using HCl, let's use, sorry, got a sneeze coming. Shoo, excuse me. All right, let's use H3O plus. Now in your text, this is probably going to be written as H2SO4, but just remember that H2SO4 is always in water, so aqueous conditions are implied when your reagent is H2SO4. This reaction is going to proceed in exactly the same way as the reaction with HCl above. That is, in the first step, pi electrons will attack the hydrogen, and you're going to get an intermediate. You're going to choose deliberately to put the hydrogen on the less substituted carbon so that the more substituted carbon can have the positive charge. Oops, I didn't want that one. I'm using lines instead of dashes and wedges because I don't want to draw the two enantiomers of that carbocation, and it's drawn above for you, so we're simplifying here. Now that you have the tertiary carbocation, water acts as a nucleophile and attacks the positively charged carbon either from above or below. That gives you this intermediate oxonium ion where the oxygen of what used to be the water molecule is now attached to three things and is positively charged. Then we're actually going to regenerate our acid by having water remove a proton from the oxonium ion. And then we will get these four products. you're going to get the syn products, and there are two of them, and they are enantiomers of each other. And then you'll get the anti-products, and there are two of them, and they are also enantiomers of each other. All of that's communicated by this drawing. Okay? So when you use acid, either HCl or H2SO4, to add electrophiles to alkenes, you get no syn-anti stereoselectivity. That is, you get both syn and anti diastereomers. But you do get regioselectivity for the OH group or the Cl group or the Br group or whatever the nucleophile is in the second step. You do get selectivity for that group ending up on the more substituted carbon, with hydrogen ending up on the less substituted carbon. And we'll call that Markovnikov regioselectivity. So that's a pattern. Now, these reactions we just did have two different names. One is called hydrohalogenation, because you're using HCl and adding that to adding a hydrogen and a halide to an alkene. And then what I just showed you is called acid catalyzed hydration of an alkene, where you're adding a hydrogen and an OH group, or in other words, adding water to the alkene. But you shouldn't see these as two separate reactions. You should see them as the same reaction with a minor detail difference between the two. Okay, questions about that one? Yeah?
What's the hydrogen from the hydrogen with that water? Why does it bond to the bottom carbon, not to the top carbon?
Right. Why does the hydrogen from the water go with carbon B instead of carbon A? Let's look at the difference. Let's suppose the hydrogen went to carbon A instead of B, and let's compare those two carbocations. What difference do you see between these? What kind of carbocation is this? That's a tertiary carbocation. The other option is a secondary carbocation. Remember, you're going to treat deuterium as identical to hydrogen. So you would call this a secondary carbocation. The tertiary carbocation is more stable. So that's the preferred intermediate because it's more stable. Anybody remember why tertiary carbocations are more stable? Ha, sigma good, to P hyperconjugation. This hyperconjugation is sort of the pray and read your scriptures answer of the organic chemistry class. So it will often be the answer to things. And we're not just making that stuff up. It's legitimately the answer, in the same way that praying and reading your scriptures is legitimately the answer. All right. So yeah, the idea is if the hydrogen went on carbon A instead of carbon B, you would get the less stable carbocation. Yes?
Would you also get products with the secondary carbocation?
Would you also get products from the secondary carbocation? No. Yep. All right, others? Yeah.
If something is syn or anti, is that all we need in comparison to the enantiomer? Like, can you be just anti by yourself?
When something is syn or anti, syn or anti just refers to the relationship between the two groups. So yes, you could say this product here is a syn product. The two enantiomers, A and D, are both syn products, but each one individually is syn, and you can tell that. The two anti-products are enantiomers of each other, but one anti-product is a diastereomer of a syn product. So, and we can illustrate that A and B and C are diastereomers. A is a diastereomer of B and C, and D is a diastereomer of B and C. Does that help? Okay, others? All right, well, now we want to do a reaction where we're going to see there is selectivity for where there is selectivity for anti-products. And I would say, actually, we won't call it stereoselectivity because the mechanism makes it be this way. So we'll call it stereospecificity for anti-addition products. We're going to see the thing that gets attacked first and the thing that attacks second end up on opposite sides of the original alkene. So this reaction is called halogenation. And for halogenation, this is reacting Br2 or Cl2 with an alkene. And you're going to see that the two things that get added to carbons A and B of the alkene are the same atom. So we're going to add 2 bromines to the alkene or 2 chlorines to the alkene. Because of that, issues of regioselectivity go away, right? Like, who cares? Because both A and B get the same kind of atom. But the issue of stereospecificity matters. So I'm going to give you an example where A and B are identical to each other. And again, it's not going to matter it's not going to matter which carbon gets which bromine. We're going to see in this reaction stereospecificity for anti-products. And what that tells you is, mechanistically, there can be no carbocationic intermediate. If there were, you would expect to see addition from both above and below. You get the same mixture of syn and anti-products that we've seen before. All right, well, let's see if we can predict what the first step of the reaction is. Your nucleophile is the alkene. Your electrophile is bromine, Br2. The HOMO of your nucleophile is the carbon-carbon pi bond. And the LUMO of your electrophile is the bromine-bromine sigma star. So it seems pretty clear that the first step in the reaction must be pi electrons attack the bromine-bromine sigma star and the bromine-bromine bond breaks. Now, if that's all that we did, we would be doing exactly what had been done for the 2 previous reactions. So far, the arrows that we've drawn would indicate that one of the 2 carbons, A and B, or B, A or B, gets the bond to bromine and the other gets a positive charge. That's a problem, though, because the mechanism says, and I'll just fast forward ahead, the mechanisms or the results of the reaction say that we only ever see the products of anti-addition. Notice how the 2 things that have been attached to the double bond are on opposite sides. And if we had gone through a carbocation, there's no way we could only get anti-products. We would, in the second step, we would have the nucleophile attacking from above or below. Does that make sense? The fact that we only see anti-products and no syn products tells us that there cannot be a carbocationic intermediate. That's really important for you to understand, because otherwise what I'm going to show you doesn't necessarily make a lot of sense. So you form a carbon-bromine bond with one of the two carbons, and at the same time as that bond is forming, because bromine is so large, it's decent at spanning the distance between the two carbons, and so at the same time, a lone pair from bromine will form a second bond with the other carbon. So what you have to understand is going on in this step is pi electrons form a sigma bond with bromine. As they do that, the other carbon of the of the original pi bond should start to have some positive charge on it. And before a full positive charge can form, the other one of the lone pairs on bromine just goes in and forms a sigma bond with that other carbon. Yeah?
So is the reason that you only get anti-products because it's more favorable for the bromines to be further apart, or why is it that?
So let me show you that. Yeah, why do you get only anti-products? The intermediate that you get after this process, if we were to draw that intermediate, it would look like this. This is going to look, to your mind, a little bit like an epoxide in the sense that it's a three-membered ring with one of the atoms in the three-membered ring being a heteroatom. I've shown you the intermediate that happens when the top face of the alkene gets attacked or attacks. So this is the result of attack from the top face. I will show you the result of attack from the bottom face, but you will see pretty quickly that they are identical and are just a pancake flip away from each other. So this intermediate is called a bromonium ion. If it were chlorine, it would be called a chloronium ion. And notice there's no positively charged carbon. There's no empty p orbital on a carbon. Yeah?
Are these happening simultaneously on top of each other, or are they separate?
These two?
Yeah.
These two are actually the same product, but the same intermediate. If you take the one on the bottom and flip it over, it's identical to the one on the top. The alkene is going to react from the top face or the bottom face. It just so happens that the products of that are identical to each other.
Because I'm picturing eventually one will break off and go down and the other will go up. Is the other bromine there too?
Yeah, the other bromine, so this where we get the second bromine, that's the second step. Yep, yeah, that's coming. All right, other questions? So what we're going to do now with this bromonium ion is we're going to open it up via an SN2 reaction with backside attack and inversion of configuration in the exact same way that we opened up an epoxide previously. So this is going to be analogous to epoxide opening. So I told you before A and B are identical, so it really doesn't matter which of those two carbons gets attacked. We attack carbon B, and that gives us this enantiomer. If we happen to attack at carbon A instead, we would get that enantiomer. Alternatively, if you want to draw it this way, you can show the enantiomer on the bottom by having Br minus attack at this carbon. Inversion of configuration means that where the bromine, the second bromine attacks, where bromine, the first bromine, the blue bromine used to be a wedge, the purple bromine is now a dash, and vice versa. Okay, do you see the analogy between that and what you saw for epoxide opening previously? Do you see that inversion of configuration? And do you see how the fact that there is no carbocation means that the bromine can only come in from one side, the back side? And that's why we just get anti-products. Questions there? Yeah.
What happens if the two sides are not identical?
If the two, what happens if the two sides are not identical? We can do that. It's difficult to tell. Well, I'll show you what we think. I'll show you what we think is happening without worrying about what the evidence for it is. I'll show you the evidence a little bit later. So if you take an alkene like this, where there is a difference between the two sides, and then you do the same thing. So pi electrons attack. By the way, when you draw the arrows this way, it's really impossible to tell which pair of electrons becomes which bond. You just don't worry about it. In other words, does it matter that this arrow comes from carbon A or comes from carbon B? No. It just is one of the two, and then the lone pair attacks the other carbon. So you can show this, you can show what I've just drawn, and that's totally fine. You can also show it this way, where let's have us attack, making it look like carbon B gets the thing, and then carbon there. There's zero difference in, there's no difference in meaning in terms of how I draw those arrows. Okay, so this is one bromonium ion. This is what would happen if the top face of the alkene attacked the bromine. And then we need to draw the enantiomer of this bromonium ion. This is what we would get if the bottom face of the alkene reacted with bromine. So you're seeing that carbons A and B are different. When A or B are different, there's evidence that suggests that the second bromine that attacks does so on the more substituted carbon. This is going to be analogous to epoxide opening under acidic conditions. And you should look at that bromonium ion with the positive charge on the bromine and say, hey, that's not so different from an epoxide that's protonated. Okay? And if you recall, when we opened up epoxides that were protonated, we opened them on the more substituted carbon. So the bromine nucleophile should attack the more substituted carbon, because that's where delta plus, build up a positive charge, is most stable. Recall that with protonated epoxides, and now for bromonium ions, though the bromine has the positive formal charge, a lot of that should be on the adjacent carbons, and more of it should be on the more substituted carbon, because positive charge is more stable on the more substituted carbon because of hyperconjugation. So there's evidence that Br minus will selectively attack the more substituted carbon, and then you'll get the two products that you would expect. One which looks like this, and the other looks like this. Now notice they are both anti-products because the bromines are on opposite side. And notice that those two products are enantiomers of each other. Also notice that because both carbon A and B get bromine and all the bromines are identical, you can't really tell which carbon the bromine attacked in the second step. But I'll show you why we think that the bromine attacks the more substituted carbon in the second step. I'll show you the evidence for that in just a second. That answer your question? Okay. Others? Okay, well, let's talk about what that evidence is. So imagine that you do this reaction. Bromine is a liquid. It's kind of nasty. You don't really want to deal with it. It's a really good electrophile, and so you have to use it in a fume hood. But it's a liquid. So you can just drip bromine liquid into a mixture, into your solution of your alkene, and just do the reaction like that, and you will get mostly or exclusively the anti-products. But sometimes it's convenient to have a solvent, and people discovered early on that if your solvent was also a nucleophile, even a weak one, it could actually compete with the halide in the second step and replace the halide nucleophile in the second step. Let me show you what I mean by this. And we'll use this same cyclohexene starting material because it illustrates the issues. So let's imagine, and just for fun, let's change it up and use chlorine, which is a gas instead of a liquid. Let's use chlorine. And then let's have our solvent be water. We could have chosen an alcohol, but basically water is our solvent, and it also happens to be a weak nucleophile. So in the first step of the reaction, this is going to be identical to what you've seen before. That is, pi bond attacks chlorine, chlorine sigma star, lone pairs on chlorine attack the other carbon, and the chlorine-chlorine bond breaks. And you get a chloronium ion. And you're going to get both enantiomers. I'm going to indicate that here to save time with a little plus or minus in parentheses, which just means both enantiomers. I want to continue to show dashes or wedges to illustrate the anti relationship between the groups that get added. So here's your chloronium ion. Now, if we didn't have water as our solvent, we would use chlorine as a nucleophile in the second step. However, water is present as our solvent, and that means it's present in vast excess, which means that it outcompetes Cl- in the second step of this reaction. So now, instead of Cl- attacking, it's water that attacks the chloronium ion. How can you tell that this will happen? Well, when someone writes Cl2 and H2O, you can assume that there's enough H2O present to outcompete the chlorine, the Cl- in the second step. So we'll just show water as a nucleophile attacking, again, in SN2 fashion, backside attack at the more substituted carbon. So again, let's illustrate this. SN2 backside attack with inversion of configuration, but attack is at the more substituted carbon, just like with protonated epoxide opening, because the partial positive charge is more stable there. And this is actually the evidence that in the second step, the nucleophile attacks the more substituted carbon, because you can now tell the nucleophile is different from chlorine. So carbon B gets the Cl, and then carbon A gets the water nucleophile. This is because water attacked as a neutral molecule, it's now bonded to three things, so this is now an oxonium ion. And in the last step, another molecule of water will remove the proton, and I'm going to keep using the pluses and minuses to indicate enantiomers. And you'll see that the two products are, and now I'll actually draw both enantiomers to be as clear as I possibly can. Oops, that's bogus. Wow, how about that? Okay, so notice that we only get anti-relationship between the Cl and the OH. So we get exclusively anti-products. So that's the stereochemical outcome of the reaction. It's stereospecificity because the mechanism requires the two groups to be anti to each other. And then we get regioselectivity. The nucleophile in the second step ends up on the more substituted carbon. And this happens analogously, it's analogous to opening of a protonated epoxide. All right, are there questions about that? Yeah, go ahead.
I might just be looking at this wrong, but in the step where the water attacks the alpha carbon,
Yep.
isn't that a tertiary carbon?
Yes, it is.
How does SN2 happen there?
So how does SN2 happen at a tertiary carbon? We dealt with this when we were talking about epoxide opening. And the idea is we're going to take a slightly different view of this molecule. We're going to look at it from this side. So from that perspective, the chlorine is going to be up, carbon A is going to be here, and B is going to be there. A methyl group should be coming out towards us here. A hydrogen should be coming out towards us here. Oops, that should have been a wedge, sorry. And then the dashes here are just going to be the atoms of the ring. Okay? The idea is that the positively charged chlorine, that's a positive formal charge on chlorine, but chlorine's more electronegative than carbon, so you know that a lot of that positive charge is going to have to be on one or both of the adjacent carbons. Of course, if the carbons are identical to each other, then they would have the same amount of partial positive charge on them. But in this case, they're not. One is more substituted than the other. And a partial positive charge is more stable on a more substituted carbon. So you will see even before the reaction happens, chloro is actually leaning. It's still bonded to both carbons, but it's bonded more tightly to carbon B, and it's leaning away from carbon A. My drawing doesn't really communicate that. Maybe I just need to make it. Now it really looks like it's leaning, okay? So the idea is that the bond between A and chloro, the more substituted carbon and chloro, is longer and weaker because carbon A can better tolerate a positive charge. If you think about what the consequences of having a longer and weaker bond might be, it's that carbon A should start to rehybridize and be somewhere between sp3 and sp2. And what that means is that when a nucleophile starts to come in, it's not as sterically hindered because that carbon has started to flatten out. Yeah. Okay, what else? Yeah.
Water also a weak nucleophile?
Water is a weak nucleophile, but the chloronium ion is a highly reactive electrophile. So it turns out water can do SN2 in this case, which is kind of interesting. This is why we sometimes call this an SN2, an SN1-like SN2. Not only because of the attacking the more substituted carbon, but also because even weak nucleophiles are okay. Saw another hand? Yes? Go ahead.
The products of this reaction we just drew, are those enantiomers or just
Those are enantiomers of each other. Yeah, so the two products are enantiomers. And I just wanted to illustrate this point. When you remember before with the hydrohalogenation and the hydration reaction where we got both a mixture of syn and anti products, it was totally okay to draw our product like this, because those just straight lines without dashes and wedges there communicate both possible stereochemical configurations at carbons A and B, 4 different products. You can't do that when you just get anti-products. If I had drawn this like, if I had attempted to draw the product like this, I completely lose the idea that OH and Cl are anti to each other. So I can't draw the product of this reaction correctly like this. I have to draw either both of them, or I could draw one of them with the plus minus symbol, or I could write plus it's an enantiomer, and that would be sufficient. But you can't just use lines when you mean to communicate that you just get the anti-diastereomer. Okay? All right. So your book will call halogenation, and then what we've just done is called halohydrin formation. A halohydrin is the name of the product that has an OH and a halide on adjacent carbons. You don't need to think of that as a separate reaction from halogenation. It's the same thing, only the nucleophile in the second step is a little bit different. So don't try to memorize that as a separate reaction. See the similarities. In that way, we've only really done 2 reactions in this chapter so far. One other thing I want to illustrate, it's not in your book per se, but it's something that's pretty easy to understand. If you were to take the same starting material, we're really bored with this cyclohexene starting material, so we need to change it up. And you were to use an alcohol in the second step, you would get as a product, and I won't draw the mechanism, but you would expect to get as a product this ether where the methoxy group acted as a nucleophile in the second step to open the bromonium ion, and those two are and then you would get the other enantiomer. You would expect to get, again, regioselectivity for the nucleophile at the more substituted carbon, and then you would expect to get the anti-relationship between the bromine and the nucleophile. So this product isn't technically a halohydrin because the thing that attacked was not water but an alcohol. I don't know what this product is called, but if you do it in exactly the same way as you do the reaction I showed you previously. And there'll be some examples on your problem set that'll have you use an alcohol instead of water as a nucleophile in your second step. Okay, so that's 4 new reactions in chapter 10. Technically only 2, as we've talked about. The next thing we want to deal with, and this is a little bit challenging, is we want to get a syn addition product where two things that are added to the pi bond of the alkene are added syn to each other. And the second thing we want to get is we want to get an alcohol, we want to have an OH group on the less substituted carbon. So we want syn stereospecificity, and we want what we will call anti-Markovnikov regioselectivity. The conditions for this reaction are as follows. We're going to use the same cyclohexene ring just because it illustrates all of these issues really well. This reaction is called hydroboration and plus oxidation. Two different steps. Hydroboration uses BH3, and then in the second step, oxidation uses sodium hydroxide and hydrogen peroxide. Now, we won't learn the mechanism for the oxidation step. It's known, and it's actually written in your study guide if you want to see it, but I'm not going to ask you questions about it. However, we will learn the mechanism for the first step. But what I want you to see, if I show you the products of this reaction, the hydrogen and the OH end up on the same side as each other. And importantly, the OH is on the less substituted carbon. And that's backwards from how we did things originally with acid catalyzed hydration. And I will explain that mechanism to you later, next time. So have a good Monday, and I will see you on Wednesday.